stable equilibrium, then if you disturb them, they rock back and forth. And there's two simple examples. The standard textbook example is this mass and spring. This spring has a certain natural length, which I'm showing you here. It likes to sit there, but if you pull it, so the mass comes here, you move it from x equal to 0 to a new location x, then there is a restoring force, F, which is minus kx. And that force will be equal to mass times acceleration by Newton's law. And so you're trying to solve the equation d2x over dt squared equals minus k over m times x. And we use the symbol omega squared equals k over m, or omega is square root of k over m. And what's the solution to this equation? I think we did a lot of talking and said, look, we are looking for a function which, when differentiated twice, looks like the same function up to some constants. And we know they're trigonometric functions. Then we finally found the answer. The most general answer looks like a cosine omega t minus phi. A is the amplitude, phi is called the phase. That tells you what your clock is doing when x is a maximum. And we can always choose phi to be 0. That means when the time is 0, x will have a biggest value, a. This is an example of simple harmonic motion. But it is a very generic situation. So I give you a second example. Now we don't have a mass. We have a bar, let's say, suspended by a cable hanging from the ceiling. And it's happy the way it is. But if you come and twist it by an angle theta, give it a little twist, then it will try to untwist itself. So now we don't have a restoring force, but we have a restoring torque. What can be the expression for the restoring torque? When you don't do anything, it doesn't do anything. So it's a function of theta that vanishes when theta is 0. If theta is not 0, it will begin as some function of theta, with the leading term will be just theta. But now you can put a constant here, it will still be proportional to theta. And you put a minus sign for the same reason you put a minus sign here, to tell you it's a restoring torque. That means if you make theta positive, the torque will try to twist you the other way. If you make theta negative, it will try to bring you back. So you have to find this kappa. If you find this kappa, then you can say minus kappa times theta is I times d2 theta over dt squared. Mathematically, that equation is identical to that. And theta then will look like some constant. You can call it a cosine omega t minus phi. And omega now will be the ratio of this kappa to the moment of inertia. Because mathematically, that's the role played by kappa and I. They're like k and m. Now, if someone tells you this is kappa, then you're done. You just stick it in and mindlessly calculate all the formulas. You can find theta, you can take derivatives, and so on. Sometimes they may not tell you what kappa is. In the case of a spring, they would have to give you k. Or they may tell you indirectly, if I pull the spring by 9 inches, it exerts a certain force. They're giving you F and they're giving you X, and you can find K. But in rotation problems, the typical situation is the following. Let us take the easiest problem of a pendulum. If a pendulum is hanging, say, a massless rod with some mass m at the bottom. So it's very happy to stay this way. If you leave it like this, it will stay this way forever. No torque, no motion. Now you come along and you disturb that by turning it by an angle theta. If you do, then the force is like this. The separation vector r from the pivot point is this. And r cross f will be non-zero because the angle between them is not 0. And you remember the torque is equal to r f sine theta. And I told you for small angles, this can be r f theta. And r happens to be, in this problem, the length of the pendulum. So it's really minus mg L theta. So you have to do some work to find theta. It wasn't just given to you in a plate. You did this piece of thinking. and you disturb the system from equilibrium and found the restoring torque, then you stare at the formula and say, hey, this guy must be the kappa I'm looking for, because that number times theta is the restoring torque. Then the omega here will be, this kappa is a generic kappa that goes into whatever it is for that problem. For our problem, kappa happens to be mgl. That's something you should understand. It's not a universal number that's known to everybody, like the spring constant of anything. In the case of mass and this pendulum, it depends on how long the pendulum is, how big the mass is. But you can work it out and extract kappa. Downstairs, you need the moment of inertia for a point mass m at a distance L from the point of rotation. It's just ml squared. So you can cancel the L, you can cancel the m, and you get omega as root of g over L. And I remind you guys that omega is connected to what you and I would call the frequency by this 2 pi f, or what you and I would call the time period by 2 pi over t. Okay, so this is the situation. Let me give one other example. Then this is a homework problem, but I want to give you a hint on how to do this. Don't take a pendulum with all the mass concentrated there. Take some irregularly shaped object, a flat planar object. You drive a nail through it there, hang it on the wall. It'll come to rest in a certain configuration. And you should think about, where will the center of mass be if I hang it like this on the wall? Center of mass is somewhere in the body here. So I want you to think about it. I'll tell you in a second. The center of mass, I claim, will lie somewhere on this vertical line going through that point. I know that by default, because the center of mass were here, for example. We know all the force of gravity can be imagined to be acting here. Then if you do that separation and do the torque, then you will find this is able to exert a torque around this point. But that cannot be in equilibrium. So the center of mass will always will align itself. The body will swing a little bit and settle down, the center of mass somewhere there. If you now disturb the body, I don't want to draw another picture, but I'll probably fail. This is a rotated body off from its ideal position. Then there will be a torque. What will the torque be? It will be the same thing, minus mg L sine theta, which I'm going to replace by theta. L is now the distance between the pivot point and the center of mass. That's your tau. So you can read the kappa. In fact, it's just like the pendulum. In other words, as far as the torque is concerned, it's as if all the mass were sitting here. The difference will be in moment of inertia. The moment of inertia of this is not ml squared. So don't make the mistake. All the mass is not sitting here. All the mass is sitting all over the place. So you should know that if you want the moment of inertia, it is I with respect to center of mass plus this ml squared. That's the old parallel axis theorem. So take that moment of inertia, put that into this formula here, take this kappa and put it there, you'll get some frequency. That's the frequency with which it'll oscillate. So every problem that you will ever get will look like one of these two. Either it's something moving linearly with a coordinate that you can call x, or it's rotating or twisting by an angle you can call theta. And if you want to find out the frequency of vibration, you have to disturb it from equilibrium, either by pulling the mass or by twisting the cable or displacing this pendulum from its ideal position here, then finding the restoring torque. Yep?
What can we say about the restoring torque in the twisting example? I mean, how do we describe that? Other than
That's a very good point. His question is, if I give you a cable and I twist the cable by some angle, how are we going to calculate restoring torque? Here is the good news. This problem is so hard, we will give it to you. In other words, that is, of course, an underlying answer. Given a cable made of some material and its torsional properties, how much of a torque you will get if you twist it by some amount. But it's not something you can calculate from first principles, so they will simply have to give it to you. Okay, in such problems. The only time you will have to find the torque on your own is in a problem like this, where I believe you know enough to figure out the torque. Okay, what you will find is, if you leave it alone, it will go to a position where there is no torque. if you move it off that position, there will be a torque. And the torque will always be proportional to the angle by which you displaced it. You read off the proportionality constant, and that's your kappa. By the way, this is not a problem. You should look at the forces, too, which is pretty interesting. This body, when it's hanging in its rest position, has two forces on it. The nail, which is pushing up, and the weight of the body, which is pushing down, and they cancel each other. The nail will keep it from falling. The nail will not keep it from swinging, because the force of the nail, acting as it does at the pivot point, is unable to exert a torque. Whereas the minute you rotate the body, mg is able to exert a torque. That's why if you twist it, it'll start rattling back and forth. All right, so what I'm going to do now is to go over more complicated oscillations using some of the techniques we learned last time. So here is the mega formula. I'm going to give it to you guys. You're allowed to tattoo it on your face. You can carry it with you. I will allow you to bring it, but you cannot forget this formula. I think you know the formula I'm driving at. Ready? E to the I x, or theta, I don't care. Let me call it theta here, is cosine theta plus I sine theta. That's the great formula from Euler. From this formula, if you take the complex conjugate of both sides, that means change every I to minus I, you will get e to the minus I theta is cosine theta minus I sine theta. That also you should know. If you got this in your head, by the way, this is something you're not going to derive on the spot. It takes a lot of work. So this is something, if you tell me, what are the few things you really have to cram that you don't want to carry in your head? Well, this is one of them. Okay, this is a formula worth memorizing. Unlike formula number 92 of your text, it's not worth memorizing. This is worth memorizing. Once you got this, you should realize that in any expression involving complex numbers, you can get another equation where every I is changed to minus I. That will give you this one. That's called complex conjugation. I generally said if you have a complex number z, z star is equal to x minus iy if z is equal to x plus iy. So in our simple example, this fellow here is z, this is the x, and this is the y. Now you should be able to invert this formula. To invert the formula, you add the 2 and divide by 2, then you will find cosine theta is e to the I theta plus e to the minus I theta over 2. If you subtract and divide by 2i, you will find sine theta is e to the I theta minus e to the minus I theta over 2i. In other words, my claim is that this funny exponential, sum of two exponentials, is the familiar cosine. It will do everything your cosine will do. It will oscillate. Sine square plus cosine square will be 1. It will satisfy all the trigonometric identities, like sine 2 theta is 2 sine theta cos theta. Everything comes out of this expression. So you should know, here is the main point you should learn. We don't need trigonometric functions anymore. Once you got the exponential function, provided you will let the exponent be complex or imaginary, you don't need trigonometric functions. This is one example of grand unification. People always say, Maxwell unified this and Einstein tried to unify this. Unification means things that you thought were unrelated are in fact related, and there are different manifestations of the same thing. When we first discovered trigonometric functions, you know, we were drawing right angle triangles, an opposite side and adjacent side. Then we discovered the exponential function, which, by the way, was computed by bankers who were trying to calculate compound interest every second. The fact that those functions are related is a marvelous result, but it happens only if you go to complex numbers. So this is another thing you should know. Okay, now armed with this, we are ready to do anything we want. Let me just tell you that every complex number z can be written as its absolute value times some phase. In other words, if my complex number z is here, it is x plus iy. That's one way to write it. You can also write it as its absolute value e to the I phi or r e to the I phi. R is the radial length, which also happens to be the length of the complex number. That's called the polar form of the complex number. X plus iy is the Cartesian form of the complex number. I may have called them r and theta or r and phi. I just don't remember. I'm going to use these symbols back and forth because people do use both the symbols, which is why I'm sometimes calling this angle as theta and sometimes this angle as phi. But the basic idea is the same. This entity here can be written either in this form or in this form. This is something you should know. If you don't know or don't understand, you should stop and ask, because everything is built on this. So what I'm going to do now is to go back to this rather simple equation, d2x over dt squared equal to minus omega squared x. By the way, today I'm going to call this omega as omega naught. It's the same guy. I'm going to call it omega naught because we will find as the hour progresses there are going to be many omegas in the game. 2 more omegas are going to come in. So we got to be able to tell them apart. As long as there's only one omega in town, you just call it omega. If there are many, you call this omega naught to mean it's the frequency of vibration of the system left to its own design. When you pull it and let it go, what's the frequency, or angular frequency? That's what we call omega naught. Now, how did we solve this equation? The way I try to solve it for you is to say, turn it into a word problem. I'm looking for a function, x of t, with the property that 2 derivatives of the function look like the function, and we raked our brains and we remembered, hey, sines and cosines of the property. 1 derivative is no good, turn sine into cosine. But 2 derivatives bring back the function you started with, which is why the answer could be sines or cosines. But now I'm going to solve it in a different way. My thinking is going to be, I know a function that repeats itself even when I differentiate it once. Namely, the function has the property its first derivative looks like the function itself. It's obvious that its 92nd derivative will also look like the function, because taking the derivative leaves the function alone except for pulling out some numbers. So why not say, I want an answer that looks like this. X equals some a e to the alpha t. That certainly has the property that if you take 2 derivatives, it's going to look like e to the alpha t on the left-hand side and e to the alpha t on the right-hand side. And then you can cancel them and you got yourself a solution. Do you guys remember why I didn't follow this solution for the oscillator? Why was it rejected? Yes? Ah, that's a very good point. So maybe I will take e to the minus alpha t. How about that? Will that give me a second derivative which is negative? You didn't fall for that, right? Because first time you'll get minus alpha, but second time you'll get plus alpha squared. That's correct. So this function is no good. Also, it doesn't look like what I want. Even without doing much mathematical physics, I know if you pull the spring, it's going to go back and forth. Whereas these functions are exponentially growing or exponentially falling, they just don't do the trick. But now we'll find that if you're willing to work with complex exponentials, this will do the job. So we're just going to take this guess and put it in the equation and see if I can get an answer that works. Okay? This is called an Ansatz. Ansatz is something we use all the time. It's a German word. I'm not sure exactly what it means, but we all use it to mean a tentative guess. That's what it is. If you're lucky, it'll work. If you're not lucky, that's fine. You move on and try another solution. So we're going to say, can a solution of this form be found with a and alpha completely free? Maybe the equation will tell me what a and alpha should be. So let's take it, put it here. By the way, I'm going to write this equation in a form that's a little easier. X double dot is minus omega 0 squared x, but each dot is a derivative. It's just more compact that way, rather than to write all of this stuff. So let's take that guess and put it here and see what we get. I get, when I take 2 derivatives, you can say, do I want e to the alpha t or e to the minus alpha t? You will find it doesn't matter, so I'm going to take e to the alpha t and put it in. Now, the beauty of the x function now is if you take 1 derivative, x dot, I hope everybody knows the x dot of this is a e to the alpha t, and x double dot is another alpha, a alpha squared e to the alpha t. That's the beauty of the exponential. The act of differentiation is trivial. You just multiply by the exponent, alpha. So if this being the result of taking two derivatives, let me write it here now. What do I get? So I'm going to go to x double dot equal to minus omega 0 squared x. Into that, I'm going to put in the guess x equals a e to the alpha t. And what do I find? I find that it's, in fact, let me write the equation in a nicer way. X double dot plus omega 0 squared x has to vanish. I just brought everything to one side. Now put e to the alpha t, a to the alpha t as your guess. Then you find it's alpha square a e to the alpha t plus omega 0 squared a e to the alpha t has to be 0. So we know what to do. Let's group a few terms. So this means I get a times alpha squared plus 1 e to the alpha t has to vanish. If you can make that happen, you've got a solution because you've satisfied the equation. No one's going to say, well, you got it by guesswork. Well, it turns out solving differential equation is only guesswork. There's no other way to solve the equation other than to make a guess, stick it in, fiddle with the parameters, see if it'll work. So we're not done yet because we want this to vanish. How many ways are there to kill this answer? You can say maybe a is 0. If a is 0, you got what's called a trivial solution. Yes? Yes. Thank you. Yep. Thank you very much. So this one is alpha squared plus omega 0 squared. Does everybody follow that? Yes. From here to here, it's very clear what to do. So we cannot kill A. Yep. Yeah. I'm trying to rule out certain options I don't like. The option I don't like to get this to be 0 is to say that is 0. That's not happening. E to the alpha t is not going to vanish. Maybe it'll vanish for some negative infinity time, but I want this to be true at all times. The equation has to be obeyed at all times. Well, this guy certainly is not 0 at all times. So the only way to fix that is to have alpha squared plus omega 0 squared equal to 0. That's the only solution which is not a trivial solution. Well, that's a simple equation, right? It's a quadratic equation. That means alpha squared is minus omega 0 squared, or alpha is plus or minus I omega 0. So when we were young and we didn't know about complex numbers, we will come to this stage and we will quit and say, look, exponentials won't work. But now we're not afraid of complex exponentials. So we embrace the solution. So now I've got two solutions. By the way, what's the value of A? Think about this. If this condition is satisfied, you realize A can be whatever you like. A is completely arbitrary. So what this equation has told me is the following. Yes, there are solutions of this form. For A, you can pick any number you like. In fact, real or complex, it doesn't matter. The equation is satisfied. But your alpha is not an arbitrary number. It can be only one of two numbers, plus I omega 0 or minus I omega 0. So we got a problem now that I look for one answer, I got two. So I will write them both. So let's say that's the solution x1 of t, which is some number a e to the I omega 0 t. Then I got another solution x2 of t, which is equal to any other number b e to the minus I omega 0 t. Now I think you guys can see in your head that if you take this and you put it in the equation, it works. And if you take this and put it in the equation, that also works. Because when you take two derivatives, I omega whole square will be minus omega square. Minus I omega naught whole square will also be minus omega naught square, so both will work. Now we have to ask, how do I decide between that solution and that solution? It turns out that we don't have to pick. We can pick both. And I'll tell you what I mean by we can pick both. Now, this is a very, very important property for all of you who are going into economics or engineering or chemistry. This or other disciplines which are mathematical, the property I'm going to mention of this equation is very important. So please pay attention. This is called a linear equation. And linear equation obeys a certain property called superposition. I'll have to tell you what it is. If I give you a differential equation, 96 derivative of x plus 52 times the 37 derivative of x, blah, 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 adds up to 0. What makes it a linear equation is that throughout an equation, either you find the function x or its derivatives, but never the squares or cubes or higher powers of x or the derivatives. Okay? The function appears to first power, not to second power. For example, if this was the equation you were trying to solve, that is not a linear equation. That's called a nonlinear equation. If you have a linear equation, that's a very, very profound consequence. And I'm going to tell you what it is. And that lies at the heart of so many things we do. So let me write down two solutions. One of them obeys x1 double dot plus omega naught squared x1 equal to 0. Second one obeys x2 double dot plus omega naught squared x2 equal to 0. Don't even have to look at these two solutions. Take a general problem where you have a linear equation, there are two solutions. Add the two equations. On the left-hand side, I get the second derivative of x1 plus the second derivative of x2. Remember, that is in fact the second derivative. Now I go back to the old notation of x1 plus x2. This has to do with the fact that the derivative of a sum is the sum of the derivatives, and sum of the derivative is the derivative of the sum. Yep?
So because you have these two linear solutions, does that mean you can sort of generate infinite set of
Yes.
solutions?
I'm coming to that in a minute. I'm first doing a more modest goal of showing that their sum is also a solution. In the second term, I get omega 0 squared times x1 plus x2 equal to 0. You stare at this equation. Look, this plus this implies what I've written down, simply by adding. But say in words what you found out. What you found out is that if x1 satisfies the equation, x2 satisfies the equation, x1 plus x2, let's call it x plus, is x1 plus x2 also satisfies the equation. And the proof is right in front of you. And the key was the derivative of a sum is the sum of the derivatives. Now I'm going to generalize it more and say, suppose I multiplied all of the first equation by A, and all of the second equation by B. Well, that's certainly still true, right? You take something equal to 0, multiply both sides by A, it's still going to be 0. Now imagine adding this to this. Add this to this, and what do you get? You will find d squared over dt squared of ax1 plus bx2 plus omega 0 squared ax1 plus bx2 is 0. So here is the punchline. If you give me two solutions to this equation, I can manufacture another one by taking the first one times any number I like plus the second one times any other number I like. So the story is a lot more detailed, more complicated than it looked. It looked like there are two solutions. Actually, there's infinite number of solutions because you can pick A and B any way you like. So linear equations typically have infinite number of solutions. And you build them up by taking a few building blocks. They're like unit vectors I and j. You can take any multiple of this unit vector, any multiple of that unit vector, and this combination will also solve the equation. Just so you don't think this is going to happen all the time, let me remind you, you don't have to write this down, but at least follow what I'm saying. Suppose this quantity here was not x1, but the square of x1, and here. Okay, you don't have to write this, because this is not a linear equation. We're not interested in this. But notice, this is nonlinear, and you guys should be able to pick it up. It's nonlinear because I've got the square of the unknown. Now can you see, if I add these two equations, forget A and B, let them both be 1, I get x1 squared plus x2 squared. But that is not equal to x1 plus x2, the whole thing squared. So even though the derivative, second derivative of the sum is the sum of the second derivative, the sum of the squares is not the square of the sum. So for a nonlinear equation, you cannot add solutions. For a linear equation, you can combine solutions with arbitrary coefficients. That's the lesson you have learned today. So our harmonic oscillator equation is a linear equation. So feel free to combine them and get the following solution. X of t is equal to a e to the I omega 0 t plus b e to the minus I omega 0 t. But a and b are whatever you like. But omega 0 is the original root of k over f. But if I gave you this solution, will you be happy to take it as a solution for the mass spring system? And if not, what is it you don't like? Yes? Anybody have a view? I mean, would you take that as a good solution? Yes?
Wouldn't you need to figure out how to choose the right A and B?
In order to achieve what?
Well, because your system starts at some, like, amplitude, some
Right.
certain amplitude.
Well, he's raising a point. Let me repeat his point. A and B, of course, cannot be, in general, they're arbitrary. For this mass and this spring, you can pick any A and B you like. But on a given day, when you pull it by 9 centimeters and release it, the answer has to be chosen so that at t equal to 0, x becomes 9. And the velocity, let's say, was 0 when you released it. So when you take the derivative of this, the velocity should vanish at t equal to 0. Or maybe it'll have some other velocity. But you can fit initial coordinate, initial velocity, the two numbers by picking these two numbers. You understand that? But that's not enough. I got another problem. Yes?
It has imaginary numbers in it?
Yes, that should bother you. The answer is manifestly not real. Okay? And we know x is a real function. That is not a mathematical requirement of the equation, but it's a physical requirement that when you pull a mass by 9 centimeters and you release it, it's going to oscillate with some real x and not a complex x, so you've got to fix that. So to say that x is real really means the following. You remember in the complex world of complex numbers, a complex number x plus iy has a complex conjugate x minus iy, and the property of real numbers is that when you take that complex conjugate, nothing happens. Because I goes to minus I, if the number was purely real, it satisfies the condition z equal to z star. So real numbers are their own complex conjugates. In general, a complex number is not its own conjugate, or if you want me to draw you a picture, that's where z is, and that's where z star is, but fellows on the x-axis have the property z is the same as z star. Z star is a reflection on the z-axis, on the x-axis of z, and therefore if the number is real, it's its own reflection. So I'm going to demand that this solution, in addition to satisfying the basic equation, also is real. To do that, I'm going to find the complex conjugate, which is denoted by the x star of t. Now you want to conjugate everything in sight. The complex conjugate of a, I'm going to call a star. Complex conjugate of e to the I omega t is e to the minus I omega 0 t. Why? Because the I goes to minus I, omega 0 and t are real numbers. Nothing happens to them. And b becomes b star, and this becomes e to the plus I omega 0 t. And I demand that these two fellows are equal. If they're both equal, then I take this exponential and demand that those be the same. That means I demand that A be the same as B star. Because if A is the same as B star, this will go into this. And then I will demand that B is the same as A star. If these conditions are satisfied, X star will become X. So the trick is to take the function, take its complex conjugate, equate it to itself, and look at the consequence. Now I want to tell you that if A is equal to B star, then you don't have to worry about this as an extra condition. Because I'm your complex conjugate, you are my complex conjugate. Because the way it works is, if you took A and changed every I to minus I, right? Or if you took B, whatever its complex form was, change I to minus I, you get A. But if you do it one more time, you come back to where you are. In other words, for any complex number, if you start it and you start it one more time, you come back to where you are. Therefore, if A is equal to B star, take the complex conjugate of the left-hand side, you will find A star is equal to B star star, which is B. So you don't need these two conditions. You do need A equal to B star. Okay, so we have to put that extra condition now. So in the real world, for people who want a real answer, you want to write it as A e to the I omega 0 t plus A star e to the minus I omega t. In other words, B is not an independent number. B has to be the complex conjugate of A. Then all of you can see at a glance that this is now real, because whatever this animal is, this is the complex conjugate of that. It's got all the i's turned into minus I. When you add them, all the i's will cancel. Answer will be real. But A is not necessarily real. The complex number A, which is some complex number, has a length and it can have a phase, because every complex number can be written in this form. So if you remember that, then you find x looks like absolute value of A e to the I omega 0 t plus phi plus absolute value of A e to the minus omega 0 t plus phi. Let me write it, omega 0 t. Now maybe that's too fast for you, so let me repeat what I did. In the place of A, write the absolute value times e to the I phi. E to the I phi will combine with e to the I omega t and form this exponential. Second term will be just the conjugate of the whole thing. You don't even have to think. Now, what is this function I have? I want you to think about it. Do you recognize this creature here as something familiar now? Yes? Have any idea? Yeah. Yep.
Well, if you
pull out the A.
yeah, and then combine those.
You remember this great identity. Where is it? Here. This one. E to the I theta plus e to the minus I theta is 2 times cosine theta. So this becomes 2 times absolute value of A cosine omega t plus phi. And if you want, you can call 2A as another number C cosine omega 0 t plus phi.
You mean that because the second one is not that representation is a star.
Oh, but for any complex number, you can pull certainly this number out of both.
Yes.
You pull it out, then you've got e to the I something plus e to the minus I something.
Makes it work.
So this is a long and difficult way to get back the old answer. You got this by fiddling around and guessing and arguing physically. But I want to show you that with exponential functions, you would have come to this answer anyway. So your point of view is, we don't need this. We've got no problems in life. We're doing very well with cosines. Thank you. Why do you bring this exponential on us? Well, now I'm going to give you a problem where you cannot talk your way out of this by just turning it into a word problem. The word problem I meant, we asked a word question, find me a function whose second derivative looks like itself, and you can either start with exponentials and differentiate twice, or sines and cosines. So you don't need exponentials. But look at the following problem. This is a problem of a mass, m, force constant k, moving on a surface with friction. The minute you got friction, you have an extra force. So you find m x double dot equal to minus kx, which is the old force due to the spring. Friction also exerts a force, which has got some coefficient b, but it's multiplied by the velocity. We know that. If you're moving to the right, the force is the left. If you're moving to the left, the force is the right. Frictional force is velocity dependent. So the equation you want to solve when you got friction is really mx double dot plus bx dot plus kx equal to 0. I'm going to divide everything by m. Take that m, put it here, and put it here. then I'm going to rewrite for us the equation we want to solve with friction. X double dot plus gamma x dot plus omega 0 squared x equal to 0, where gamma is just b over f. This is the equation you want to solve. Can you solve this by your usual word problem? It's going to be difficult. Because you want a function which, when I take two derivatives, looks like the function plus some amount of its own derivative. If you take cos omega t, it won't do it. If you take sin omega t, it won't do it. So we can still solve it, because even this equation you solve by the same mindless approach, which is to say, let x look like a e to the alpha t. And it'll work. Let's see how it'll work. It has to work. You can see why. Because when I take two derivatives of x, I will get alpha squared. Let me pull the a out of everything. Plus alpha gamma plus omega 0 squared e to the alpha t equal to 0. So what we learn is, yes, there are solutions of this form to this equation. Once again, a can be whatever number you like, because if a vanishes, you kill the whole solution. E to the alpha t is not going to vanish at every instant in time, so the only way is for this to vanish. That means alpha that you put into this guess is not any old number, but the solution to this quadratic equation, alpha squared plus alpha gamma plus omega naught squared equal to 0. So we want alpha squared plus alpha gamma plus omega naught squared equal to 0. So alpha must be the root of this equation. And we all know a quadratic equation will have two roots, and we will get two solutions, and we can add them with any coefficient you like. That will also be a solution. So let me write it down. So in other words, I'm going to explicitly solve this quadratic equation. So go back to the old days and remember that the solution of that equation will be alpha equals minus gamma plus or minus square root of gamma squared minus 4 omega naught squared over 2. I would like to rewrite this as minus gamma over 2 plus or minus square root of gamma over 2 square minus omega naught squared. And let's call the two roots, one with a plus sign and one with a minus sign, as alpha plus and minus. This is a shorthand for this whole combination. Do you understand that if I give you the mass and the spring constant, and I give you the coefficient of friction, the number b, alpha plus and alpha minus are uniquely known. So you will get two precise numbers coming out of this whole game. And your answer then to this problem will be x of t is any number a times e to the minus alpha plus t plus any number b times e to the minus alpha minus t, where alpha plus and minus are these two numbers. I want you to notice both numbers are falling exponentials. It's very important, because now I'm talking about a mass where I pull the spring, there's a lot of friction, and I let it go. I don't want an exponentially growing answer. That makes no sense. The x should eventually vanish. And that will in fact happen. Let's make sure you understand that. Look at these two roots, minus gamma over 2, plus and minus, well, that is this solution, minus gamma over 2 square minus omega naught square. I'm going to assume in this calculation that gamma over 2 is bigger than omega naught. Let's do that first. Then you can see that that's a negative number, that's a negative number, the whole thing is negative. So alpha minus is definitely, let me see how I wrote it. Oh, I'm sorry, I made a mistake here. I think these are called just plus and minus alpha. Alpha has two roots. and I have to write them as they are. Okay, I'm sorry. So please remove this unwanted sign there, because they are the two answers for alpha. So I put e to the alpha plus t. So again, I should change my answer here. I'm really sorry about this one. I should write it as, now I'm going to write it below so you have a second chance. So here is what it looks like. A e to the minus gamma over 2 plus square root of gamma over 2 square minus omega naught square t plus b e to the minus gamma over 2 minus gamma over 2 square minus omega naught square t.
You got the minus.
Pardon me?
You got the minus there.
I think I did mean this, or did I get it wrong? These are the two values of alpha. So they both have the first number to be minus gamma over 2. And the square root comes to the plus sign for one of them and minus sign for the other one. I probably have A and B mixed up. Let me check that. No, I think even that's okay. Yes, I'm willing to be corrected if I got A and B mixed up. I know these are correct. I want to make sure this is what I call B. B has a coefficient alpha minus, which would be this one. Oh, yes, yes. So what should I do? Call this A, call this B. How is that now? Let's see if that works out. This should be B e to the alpha minus t. B e to the minus gamma over 2 minus that, yes.
But there's also the negative number again.
Pardon me?
For the on the right-hand side. Oh, wait, no.
Okay, the point of writing it this way is to show you that both these powers, this is clearly a positive number, so it's e to the minus a negative number. I just want to show you that this object, that's all I wanted to emphasize. Inside the square bracket is also positive, because this is gamma over 2. You can see this is a number smaller than gamma over 2 square. So if you take the square root of that number, it will be smaller than gamma over 2. So this cannot overturn the sign of this. It will still be positive. Overall sign will be negative. So if you draw the picture here, it's a sum of two exponentials. It will just die down after a while. And how do I find A and B? To find A and B, what I have to do is to take extra data. One of them may be initial position x of 0 is given to me. If x of 0 is given to me as some number, I take the solution, I put t equal to 0 and have it match this. If I put t equal to 0, well, all this exponential vanish and I just get A plus B, because e to the 0 is 1. So I already have one condition on A and B. Their sum must be the initial position. How about the initial velocity? Go back to this x and take dx dt. What do you get? Dx dt is alpha plus A e to the alpha plus t plus alpha minus B e to the alpha minus t. The derivative of my answer is this. Evaluate it at t equal to 0. At t equal to 0, you put t equal to 0 here, you find x dot of 0 equal to alpha plus A plus alpha minus B. So here are the two equations you need to find A and B. Solve these two simultaneous equations. In other words, I will tell you the initial position and I will tell you the initial velocity. You will take then this number known and that number known. These are linear simultaneous equations for A and B. You will fiddle around and solve for A and B. Yes?
Are A and B still complex conjugate?
Now we have to ask the following question. In this problem, if everything is real, see previously what happened is when I took the complex conjugate of this function, the conjugate turned it into the other function. And the conjugate of that function turned back into this one. That's why A and B were related by complex conjugation. Here, if I take the complex conjugate of x, e to the alpha plus t, if it's real, remains itself. So A just goes into A star, B goes into B star, and you want the answer to be unchanged. That requires A equal to A star and B equal to B star. Thanks for pointing out that here we do want A equal to A star and B equal to B star. So what I'm telling you is go take the solution, conjugate it and equate it to itself. And remember that now this exponential remains real to begin with, so it doesn't go into anything, it remains itself. And I compared this exponential before and after its coefficient that went from A to A star. They have to be equal, so A is A star and B is B star. Yes?
Why is this real now?
Well, look at these functions. There is no complex numbers here. That's why everything is real. So what problems have I solved now? First I put gamma equal to 0, no friction. And I just re-derived the harmonic oscillator, cos omega t minus phi or plus phi. Then I took a problem with friction. Then I got a solution that was just exponentially falling. Because even though it looks like alpha plus, that's a negative number, that's a negative number, in the end both are falling. So they will, it says you pull the mass and let it go. It'll relax to its initial position, it'll stop. But all of you must know that there's got to be something in between. In the one case, I have a mass that oscillates forever. The other case, I have a mass, when I pull it and let it go, goes back to equilibrium and reaches 0 at infinite time. But we all know that the real situation you run into all the time, when you pull something and let it go, it vibrates and it vibrates less and less and less and less and then eventually comes to rest. Where is that solution? It's got to come out of this thing. Yes? That's correct. So you got to go back to the roots I found for alpha. It's minus gamma over 2 plus or minus square root of gamma over 2 square minus omega naught square. I had taken gamma over 2 to be bigger than omega naught. So what I did was I turned on friction, but I didn't turn on a small amount of friction. I turned on a rather hefty amount of friction so that the friction term was bigger than the omega naught term. But if you imagine the other limit where you had no friction and you turn on a tiny amount of friction, then the tiny gamma over 2 will be smaller than this omega naught. Of course, then you got the square root of a negative number, right? So you should really write it as, so let's take gamma over 2 less than omega naught. Then you will write this as minus gamma over 2 plus or minus I times omega naught square minus gamma over 2 squared. In other words, write the stuff inside as minus of this number now and take the square root of minus 1 and write it as I. So now what do the solutions look like? They look like x equal to a e to the minus gamma over 2. Let me write the exponentials if you like. A e to the minus gamma over 2 t plus I omega prime t, but I'm going to call this combination as omega prime. That's why we had omega naught and omega prime. Plus b e to the minus gamma over 2 minus I omega prime t. Now e to the minus gamma t over 2 is common to both the factors. You can pull it out. Imagine pulling this factor out common to the whole expression. Then you just got a to the I omega prime plus b to the minus I omega prime. That's a very familiar problem. If you want that to be real, you want a to be equal to the complex conjugate of b. Then you repeat everything I did before, so I don't want to do that one more time. You will get some number c times e to the minus gamma over 2t times cosine omega prime t plus, you can add a phi if you like, there. So what does this look like? What does this graph look like? It looks like cos omega t, but it's got this thing in the front. If gamma vanishes, then forget the exponential completely. This is our oscillating mass. If gamma is not 0, imagine it's 1 part in 10,000. Then for the first 1 second, this number will hardly change from 1. Meanwhile, this would have oscillated some number of times. But if you wait long enough, this exponential will start coming into play. And the way to think about it is, it's an oscillation whose amplitude itself falls with time. And if you draw a picture of that, I think you will not be surprised that if you draw the picture, it will look like this. It's called a damped oscillation. So that's the method by which you describe the 3 cases. One is no friction, and one is small friction or friction obeying this condition, when you have oscillatory motion whose amplitude is damped with time. Then you have the other case where gamma has crossed some threshold, when omega naught is smaller than gamma over 2, then you get 2 falling exponentials. So what do you imagine the mass is doing? With no friction, if you pull it, let it go, vibrates forever. That's not very realistic. If you turn a tiny amount of friction, it will do this, which is very ubiquitous. We see it all the time. You pull a swing and you let it go. After a while, it comes to rest. This tells you it never quite comes to rest, because as long as t is finite, this number is going to be non-zero, but it will be very small. At some point, you just cannot see it. Third option is overdamped. Overdamped is when gamma is bigger than omega naught over 2, then the answer is nothing that oscillates. Nothing oscillates. Everything falls exponentially with time. There you should imagine you pull something, let it go, it comes slowly and stops. When you buy your shocks in your car, the shock absorbers, they're supposed to damp the vibration of the car. It's got a spring, but there's suspending the tires, but it's immersed in some viscous medium so that its vibrations are damped. So when you hit a bump, if your shocks are dead, you vibrate a lot of time and slowly settle down. That's when your shocks are in this regime. When you bought them, they were in this regime. When you bought them, they were doing this. Once you hit a bump and you overshoot from your normal position, you come down to 0 and you stay there. Okay, so that's the ideal situation for damping. All right, so I'm going to the last topic in oscillation, but is there anything else? Is there anything here that you need clarification? Yes? Yes. So when gamma over 2 equals omega naught, this thing vanishes, and you seem to have only one solution, e to the minus gamma t over 2. You don't have the plus or minus, right? And we sort of know in every problem there must be 2 solutions, because we should be able to pick the initial position and velocity at will. If a solution is only one free parameter, you cannot pick 2 numbers at will. Now that's a piece of mathematics I don't want to do now, but what you can show is in that case, the second solution looks like this. It's a new function, not an exponential, but t times an exponential will solve the equation. Those who want to see that this is true can put that into the equation and check. In other words, pick your gamma carefully so that this square root vanishes. Only a gamma is left, but that gamma is not independent of omega. That gamma is equal to 2 omega naught. For that problem, you can check that that's a solution, so is that. There are nice ways to motivate that, but I think don't have time to do that. Yes? Why was A equal to A star here? You mean here? Okay, take this x. Demand that when you conjugate it, nothing should happen. Okay? In this particular example, when alpha plus and alpha minus are real numbers, e to the alpha plus t remains e to the alpha plus t when you take conjugate. So therefore, A has to remain A star, and B must also remain invariant when you take the conjugation. In other words, if this was an imaginary exponential, like in the other problem, when you take the conjugate, this exponential becomes this guy and that exponential becomes that guy. Then by matching the solution, you will be able to show this must be the conjugate of that, that must be the conjugate of this. But if no imaginary exponentials appear, each term must separately be real. Now this is something you will have to think about. I'm not saying my repeating it makes it any clearer. So what I want you to do is take the x take the complex conjugate of x, equate the two sides. That's a rule among functions that if you got e to the plus alpha t, its coefficient should match on both sides, and e to the minus alpha t should have matching coefficients. It's like saying when two vectors are equal, the coefficient of I should match and the coefficient of j should match. There's a similar theorem that if you take a sum of two independent functions equated to sum of two other same independent functions, the coefficients must separately match. If you impose that, you will find what I told you. Okay, now for the really interesting problem. The really interesting problem is this. I got the mass, I got the spring, I got the friction, but I'm going to apply an extra force, F naught cosine omega t. This is called a driven oscillator. So far the oscillator was not driven. In other words, no one is pushing and pulling it. If you of course, you pulled it in the beginning and you released it, but once you released it, no one's touching the oscillator. The only forces on it are due to internal frictional forces or spring force. But now I want to imagine a case where I am actively driving the oscillator by my hand, exerting a cosine omega t force. So omega here is the frequency of the driving force. Okay? That's why there are so many omegas in this problem. The omega prime that you saw here is not going to appear too many times. It's a matter of convenience to call this omega prime. But this omega will appear all the time. When I write an omega with no subscript, it's the frequency of the driving force. And the equation we want to solve is x double dot plus gamma x dot plus omega naught square x equal to f over m, because I divided everything by m, cosine omega t. So we've got to solve this problem. Now this is really difficult because you cannot guess the answer to this by word problem. Now you can do the following. If the right hand side had been e to the I omega t instead of cos omega t, you would be fine, because then you can pick an x that looks like e to the I omega t. Then when you take two derivatives that look like e to the I omega t, one derivative look like e to the I omega t, x itself will look like e to the I omega t, you can cancel it on both sides. But what you have is cos omega t. So here's what people do. It's a very clever trick. People say, let me manufacture a second problem. Nobody gave me this problem, okay? This is the problem you gave me. I make up a new problem, the answer to which is called y. But y is the answer to the following problem. The driving force is sine omega t. So this is what you gave me to solve. This is my artifact. I introduced a new problem you did not give me, but I want to look at this problem. Now here is the trick. You multiply this equation by any number, it's still going to satisfy the equation. Let me multiply by I. Put an I here, put an I here, put an I here, put an I here. Multiply both sides by I and add them. Then I have got x plus iy double dot plus gamma times x dot plus iy dot plus omega naught squared times x plus iy. Let's introduce a number z, which is x plus iy. It varies with time. Then this equation, by adding the two equations, look like z double dot plus gamma z dot plus omega naught squared z is f over m e to the I omega t. So I've manufactured a problem in which the thing that's vibrating is not a real number. The force driving it is also not a real number. It's the cos omega t plus I sine omega t. But if I can solve this problem by some trick, at the end, what do I have to do? I have to take the real part of the answer, because the answer will look like a real part and an imaginary part. I'll have to dump the imaginary part. That will be the answer to the question I posed. Imaginary part will be the answer to the fictitious question I posed. Now, why am I doing this? The reason is the following. If the driving force is e to the I omega t, I can make the following ansatz at guess. Z is some constant times e to the I omega t. I will show you now solutions of this form do exist. Because let me take that assumed form and put it into this equation. Then what do I get? I get minus omega square z naught e to the I omega t, because two derivatives of e to the I omega t give me I omega times I omega. Then one derivative gives me I omega times gamma times z naught e to the I omega t, and no derivative just leaves it alone. E to the I omega t equals f naught over m e to the I omega t. So let me rewrite this as follows. Let me rewrite this as minus omega square plus I omega gamma plus omega naught square times z naught e to the I omega t is f over m e to the I omega t. This is what I want to be true. Well, e to the I omega t, whatever it is, can be cancelled on two sides because it is not 0. Anything that's not 0 you can always cancel. And here is the interesting result you learn. For this equation to be valid, the z naught that you pick here in your guess satisfies the condition z naught equals f over m divided by omega naught square minus omega square plus I omega gamma. Now, parts of it may be easy, parts of it may be difficult. Easy part is to take the guess I made and stick it in the equation, cancel exponentials, and get the answer. What you should understand is x was what I was looking for. I brought in a partner y, and I solved for z, which is x plus iy, and z was assumed to take this form, with the amplitude which itself could be complex times e to the I omega t. If z naught looks like this, then z, which is z naught e to the I omega t, looks like f over m e to the I omega t divided by this number in the denominator I'm going to call I for impedance. I is called impedance, and it's the following complex number: omega naught square minus omega square plus I omega gamma. Okay, we're almost done now. So the z looks like f naught over m e to the I omega t divided by this complex number I. Imagine this complex number I. What does it look like? It's got a real part and an imaginary part. Imaginary part is I omega gamma. Real part is omega naught square minus omega square. This is the complex number I. So we are told the answer to our problem is to find this number z, then take the real part. Does everybody agree that every complex number I can be written as its absolute value times e to the I phi, which is going to be here? And I'm going to write it that way because now things become a lot simpler if you write it that way. F naught over m divided by absolute value of I e to the I phi e to the I omega t. Now this e to the I phi, I can delete it here and put it upstairs as minus I phi. So let me write it in that form. Then it's very easy. F naught over m divided by the magnitude of this I times e to the I omega t minus phi, where phi is this angle. Well, now that I got z, I know how to find x. X is the real part of z. Now, when I look at real part, all these are real numbers. So I will keep them as they are, f naught over m divided by I. The real part of this function, I hope you know by now, is cos omega t minus phi. And that's the answer. The answer to the problem that was originally given to us is the following. You know the magnitude of the applied force, the amplitude of the applied force. You know the mass of the particle. You need to find the absolute value of I and phi. For that, you construct this complex number, whose real part is this, whose imaginary part is I omega gamma. Then the absolute value of I is just, by Pythagoras theorem, omega naught square minus omega square square plus omega square gamma square. And the phase phi obeys the condition tan phi is equal to omega gamma divided by omega naught square minus omega square square is omega square gamma square. I'm sorry, it's just the imaginary part over real part. So this is the answer to the problem that was given to us. But there's one subtle point you should notice, which is the following. Where are the free parameters in this problem? Everything is determined in this problem. Phi, absolute I, all this are known, but we know every equation should have two free numbers. You know what they are? Anybody know? Okay, let me tell you what the answer to that question is. I'm saying I can add to this the solution I got earlier on without the driving force. Because in this problem, when I had a right-hand side with a driving force, let me add a 0 to that. That's harmless. And by superposition principle, if that force will produce that displacement, 0 will produce what? Well, we have seen all morning that even when the right-hand side is 0, there are those solutions I got for you, e to the gamma over 2, cos omega prime t, etc. So you can always add to this what's called a complementary function, which is the solution to the equation with no driving force, which is what we were studying earlier in the class. But usually people don't bother with this because they all have in them e to the minus gamma t over 2. So if you wait long enough, this will die out. This is the only thing that will remain. So at early times, this is not the full answer. You should add to this the answer when there is no driving force. And together, they form the full answer. And the numbers a and b that you have there will be chosen to match some initial conditions like initial position, initial velocity. Okay, now time is up. I'm going to stop. So I have not been able to finish some parts of this. So I'm trying to see what I can do. I had asked for you to give this problem set to me on, what is this today? On Wednesday, right? So you don't have enough time. I mean, I haven't taught you a few other things you need, about 5 minutes more of work. So I don't want to keep you back. So here's what I will do. I will post on the website some notes on just the missing part here. So you can read it. Then you can do 1 or 2 problems you may not be able to do without that. Then I will come on Wednesday and I will teach that to you again. But you will be able to hand in